Here's an example of a relative velocity problem in one dimension. And we have a boat that's going to travel down river from one dock to another. So I've just drawn a really simple picture here. And let's imagine that the boat's going to travel, let's say, from this dock down to this one, and then back up again. And the distance here is 1,000 meters each way. The current in this river is 2 meters per second. And so definitely, I mean, we can pick one direction for the current to go in. So let's say that the current we're going to call the velocity of the water with respect to the ground. That's what I'm going to call the current. And that is going to be 2 meters per second. That's what it gave us. And let's say that that is, let me erase my, sorry, my arrows that I had drawn here. But that's going to be 2 meters per second. And that's pointing that way. And then, but I've also got the boat and it's in the water and it's got its own motor. And so in one direction, obviously the current's going to help the boat go faster. And then when it has to go back against the current, it's going to make the boat, it's going to have to fight the current. So when we're thinking about that, you can imagine this in your head, but if we're also kind of writing out why that velocity adds or subtracts, we can back that up with an equation that we learned in class. So if we imagine that we have the velocity of the boat with respect to the water, because it's in the water with its, propeller spinning, on its way, let's say that it's going positive 10 meters per second. Sorry, I've got a lot more sig figs here. Sorry. In one direction, and then when it turns around, it will go negative 10 when it comes back, okay? So we've got to define our coordinate system. We'll say that down this way is positive, okay? So as it goes downstream, we would say that the boat with respect to the ground is equal to the boat with respect to the water plus the velocity of the water with respect to the ground. Notice here that these subscripts match. Okay, that's a good sign that I've written my equation correctly. And then let me give myself some more space here. So then, because I've got the boat going in the positive direction, along with the current on the downstream way, then I'm gonna add those two vectors. So it's gonna seem like the boat's going faster with respect to something on the ground. And then when it goes upstream, the boat with respect to the water, or I've defined my coordinate system as down as like this direction. So now I've got to go negative 10. I'm going against the current. So now I've got -8. And really, these velocities are, I'm going to change them into speeds because really then I'm calculating the time to do the round trip. Okay, so then when I've got to do that, I'm going to just take that distance and calculate the downstream part separately. So this should be a shorter time. Oops, sorry. So then when I solve for time, I end up doing 1,000 over 12, which gives me about 83 seconds. And then for the upstream portion, I'm not really worried about the negative because I guess I could say the displacement for that portion is also negative. Or I could just take absolute values since I'm looking for distance really rather than displacement. So I'm going to take absolute value here. So then when I do 1,000 over 8, I get a much larger time. So the total time added up would be the sum of those two, or about 208 seconds. Okay. Notice if it was just calm water, it would take 10 meters per second each direction without any current at all. This would be a 2,000 meter trip total, and this would be a 200-second journey. So the time that I save in the current helping me, I don't make up for that in the time that extra time that I have to fight the current. So it'd be better to have no current at all as far as time goes. I'm always losing time when I've got extra, wind or current to fight. Okay.